안녕하세요 여러분, 혜리입니다. In the previous lecture, we have talked about the basic techniques of differentiation. So remember all these formulas and some trigonometric functions, exponential, log, and some basic techniques such chain rule, product rule, and quotient rule. And for today, we're going to do some applications of differentiation using what we have learned from that. So we're going to start with finding the maximum and minimum points. So before we directly learn that, we have to learn some terminologies. So for example, let's say we have a curve like this. Then this and that. If we observe the gradient of this curve, we see that it's increasing and it becomes 0 and it decreases and becomes 0 again and increases. So we see that at these two certain points, the gradient is 0, and we call these points as stationary points. No, the gradient is 0, so it's stationary, it's not moving. And there are two varieties of stationary point. So this is called the local maximum, and this is called the local minimum. And please be aware that this is not the maximum of the entire graph, because the maximum could be somewhere, it's not defined, it's somewhere up there, right? And if the graph is restricted like this, we see that this point is greater than this local maximum, and for this point we call it as global maximum, and for this point it's lower than local minimum, so we call it as global minimum. Alright, so that's the basic terminologies that we have to know. So this means that in order to find the local maximum and local minimum, we have to find the stationary point, and we can do this by obtaining this equation. Because what dy over dx means is that dy over dx basically gives you the gradient of the original function y. So if the gradient equals to 0, and if we solve it for x, then we'll have the roots of this, and those x values will correspond to the x coordinates of these local maximum and local minimum. So let's try a question like this. So I have already prepared the questions. So here, first, find the maximum and minimum of this function. So I'll just copy down the function. Alright, so we are going to look for the maximum and minimum. So again, as I said, we have to find dy over dx, making that 0. So first, find f prime x. Then we'll have 6x squared minus 18x plus 12. Very simple, right? And if we factor, and this will equal to 0, and we solve for x, then we have this, dividing both sides by 6. So we have x equals to 2 and 1, which makes this gradient 0. But now here we have a problem, because we know these x coordinates, but we don't know which of the coordinate yields the local corresponds to the maximum or minimum. Then how do we justify it? So the first method to justify whether a point is a maximum or minimum is the first derivative test. And the word derivative means differentiated function. So first derivative means you differentiate a function once. If it's called the second derivative, then you differentiate the function twice. And if it's nth derivative, then you differentiate the function n times. That's it. So first derivative test, we are basically looking for the behavior of the gradient. What does that mean? So let's sketch the equation of the gradient again. So that will look like something like this. Right? So that's the graph of the gradient function. Now recall what I said yesterday. All these y values here correspond to the gradient of this function, right? So if this is, for example, like half, then this y value corresponds to the gradient of this function at x equals to half. Then we can see that the value of the gradient decreases, right? And it reaches 0, and it goes negative, and then goes to 0 again, and it becomes positive. So we can try to make a table. So we see that 1 and 2 are the roots of this derivative. And for f prime x, we see that when x is less than 1, it's all positive. And when x is between 1 and 2, it's negative. And when x is bigger than 2, it's again positive. And again, 1 and 2, f prime x equals to 0. Then what does this plus and minus mean? I mean, what do these plus and minus mean in the original function? So plus basically means the value is increasing because the gradient is plus. So as long as the gradient is plus, then y value of the original function must be increasing, right? And if the gradient is negative, then the value must be decreasing. And when it's positive again, then the value must be increasing. So from here, we can observe that the original function, when x is less than 1, it's increasing. And then after 1, it's decreasing back, right? Increasing and decreasing. And what is this? It's a local maximum. And same thing for this. So the value is decreasing and increasing again. So this point must be the local minimum. So this is how we can justify whether a stationary point is a maximum or minimum using this first derivative test. And also using this, we can find the domain of the original function where the function is increasing or decreasing. So for this question again, so actually it's divided into 3 parts. So first, A was finding maximum and minimum. So we have found that, right? So we have justified as well. So local maximum is at when x equals to 1. So we put this x back into the original function because we're looking for the local maximum of the original function. So we put it back, then that's so it yields 4, and local minimum is when x equals to 2, so that yields 13. Yeah. So that's how we find the local maximum and local minimum. And now, when the question asks you something like find the domain where the function is increasing or decreasing, then we can do that using this table again. So as I told you, this plus and minus in f prime x indicates the value of the gradient. So plus means the gradient is positive, so the value is increasing, right? The function is increasing. And negative means the gradient is negative. That means the function is decreasing. If the gradient is negative, that means it's in this direction, and of course it's decreasing. Positive is this direction, so it's increasing, right? So for the region, so that was A, and for B, so increasing the region, x belongs to, x is less than 1 or x is greater than 2. And if you want to use the set notation, you can write it like this, but it's up to you. And same thing, decreasing, x is between 2 and 1, or you can write it as x belongs to a set, like that. And one thing, so this inequality, it's not equal, okay? Because when x equals to 1, then the gradient is 0. Gradient is 0, that means it's the stationary point. The value is not increasing or decreasing. So it's just stationary. So we do not include these stationary points, okay? So that's why it's just either less than or greater than, no equal or, okay? So that was the first application of finding the maximum and minimum. And yeah, so that was the first test. And there's another test of doing this, called the second derivative test. So as I said, second derivative means we differentiate it twice. So instead of using the first derivative to solve it, because we've already done it, let's try using the second derivative. So first, what you have to know this. So let's say we differentiate a function once, and then when that equals to 0, I said that it yields the stationary points. The roots represent the stationary points, so x coordinate of the stationary points, right? So let's say we obtain the stationary points of x coordinates of the stationary point. And what do we do with these is that, so first compute the second derivative and put the coordinate in, put these x coordinates in. And if that value is less than 0, that means it's local maximum. And if it's greater than 0, it is local minimum. But when it equals to 0, so it doesn't have to be these two. So for any value, x value, where the second derivative equals to 0, that yields the point of inflection. So inflection. Yeah. So what point of inflection is that it looks like this. So like a cubic function. Yeah. So again, let's come back to this problem and use second derivative to solve it. So fx looks like that. Fx is that. F prime x. So f double prime will be this. And we've already obtained the roots of f prime x, 2 and 1. So here are the two candidates, and let's put these in. So if we insert 2, then it's 24 minus 18, so it's 6. Greater than 0, that means it must be the local minimum. And same thing, we put in 1, then 12 minus 18, that's negative 6, less than 0, so it must be local maximum. And it's exactly the same result as this, right? So when x equals to 1, it's the local maximum, and when x equals to 2, it's the local minimum. Done. So for the first derivative test, we can justify the local maximum and local minimum, and we can also obtain the domain where the function is increasing or decreasing. Then what about for second derivative? What can we do? We can find the concavity of a function. And what's concavity? So it's divided into concave up and concave down. So concave up looks like this, and concave down looks like that. And the function is concave down when the double prime is, so we see that when it's concave down, we have local maximum, right? And we have local maximum when the second derivative is positive. Local maximum when the second derivative is negative. So we have concave down when the double prime is less than 0. And same thing for this. We have concave up when the double prime is greater than 0. So going back to the question again. So C, using this function, we have to find the domain where the function is concave up or down. So we've already obtained the second derivative, right? So f double prime x is this. So let's sketch it up because it's very simple, right? So the roots is 2/3 3/2. Sorry. So, and it's okay, it's down there. It's not to scale. So it looks like that. It's a linear function. So we see that when x is greater than 3/2, the double prime of x is greater than 0, right? Therefore, the function is concave up when x is greater than 3/2. And similarly, when x is less than 3/2, we have the double prime negative. This is double prime. So double prime is negative, right? Then concave down when x is less than 3/2. And that's it for concavity. So it's pretty simple if you know what to do. So for concavity, just remember this. And so for finding the point of inflection, you just need to find the value of x such that f double prime equals to 0. So very simple example, it can be like x cubed, because we already know that the origin must be the point of inflection by the sketch, but let's confirm it using this property. So we differentiate it once and differentiate it twice, then we have 6x. And when this equals to 0, then x must be 0, right? And when x equals to 0, then y must equal to 0. So the origin must be the point of inflection. Simple, right? So that's it for the first application of differentiation. Now, second application we're going to do is finding the tangent and normal line of a curve. From a curve. So tangent and normal line. Then of course the equation must look like a linear function, right? Then we just need to find two things: gradient and any point on this line. Then we're done. So for example, let's say we have a function like this, and the question is very likely to ask you to find the tangent or normal at a certain point. Like they will give you the point, very likely. So let's say P, then let's say if this is T, then T and FT. So the point will be given, and we have to find the tangent here. So since the point is already given, we don't really have to care about this. We just need to find the gradient. And which gradient do we need, and how do we find the gradient? So first we need the gradient at this point, because we're looking for the tangent or normal at this point, right? And in order to find the gradient at this point, how do we find it? F prime x. What does that mean? It yields the equation of the gradient at a given domain of the original function. That means once we have f prime x, and if we insert this t value as the input, then that will be the gradient at this point. So let's try an example. So let's say we have learned log functions as well, so let's use log this time. So we want to find the tangent line at this point. So, well, if you can sketch it, it's good to sketch and do it. So it's just a horizontal shift to the left by 1 unit, right? So, and this will be this is how it looks like, and we have to find the tangent at this. So the tangent line will look like that. Then let's see. So we have the point. So first we have to find the tangent. That's the equation that we have to find, and we can find C using this coordinate later. And now we just need to find this gradient. And again, how do we find the gradient? We first differentiate the function, because the derivative yields the equation of the gradient. So if we differentiate that, you may use chain rule. So we have this. Yeah, I'll skip it because it's very simple. And so we have to find the gradient at the origin. That means the gradient of this at x equals to 0, and it yields 1 over 1 plus 0, so it's 1. Then we're done. So the gradient is 1. So this is how the curve looks like, and it must pass through the origin. So then C must be 0. Therefore, the tangent must be y equals x. Done. Very simple, right? Then how do we find normal line? So again, normal line. So normal line, again, it's a line, so it must be in a linear equation, and the point will also be given, because that's what the normal looks like. So it also passes through the point, so we don't have to worry about the point. All we need to worry about is the gradient. And how do we find the gradient of the normal? So one thing that you've learned probably in your middle school is that when you have two perpendicular lines in a number plane, then the product of their gradients must be -1. So that should be the tangent gradient, and this must be the normal gradient. That means simply the gradient of the normal equals to the negative reciprocal of the gradient of the tangent. So we can use this to find the normal line too. So that will be very simple. The gradient of the tangent is 1. That means the gradient of the normal should be -1. And again, it will pass through the origin as well. So the normal line for this question will be y equals negative x, but I'm going to try another question with you. So this one. So we want to find the normal line at this point. And again, if you can sketch it, it's always better to start with sketch. So we see that at x squared, which at x equals to 0, it has repeated roots, and another root at -2, and it's a cubic function, so it looks like that. That's how we sketch it. And 1 and 3, so it must be somewhere like here. And we want to find the normal line at this point. So if we have a tangent like that, then we want to find this. We want to find the equation of this red line. So again, differentiate it. The reason why we're differentiating is because we want to find the gradient. And why? Because differentiated function yields the equation of the gradient at any x values defined in the original function. So we first need the equation of the gradient of the tangent. So we differentiate it, and then the equation of the tangent at that point, which x equals to 1, will be 7, right? Then the gradient of normal must equal to -1/7, because again, the gradient of the tangent and the gradient of normal multiplied together must be -1. So this times that should be -1. So we have this, and we have the point. So we're done. And then we insert this point. So C must equal to 3 plus 1/7, so that yields 22/7. Therefore, the equation of the normal will be this. Done. One last application, which is very, very rare, but still very possible to get, especially for HL students. So from these two exercises, all the points here, the points given, they're on the line. So we see that the origin is 0, 0. So when you insert 0, then lone 1 is 0, so y equals to 0. So this point is on this curve. And again, this one as well. So if you put 1 there, then 1 plus 2, so it's 3. So this coordinate also lies on this curve. But very rare, but some certain circumstances, in the question, the point may not be on the line. What does that mean? So for example, you have a curve, and then you have a random point outside the curve. And then the question asks you to find the tangent on this curve where it passes through the point here. Like that. Then you may wonder, what's the difference between these two? So again, the point is given. So the tangent passes through this point. So yeah, the point is given. But the problem is, we can't find the gradients directly because we don't know where the tangent is at, right? It may be here, but honestly, it could be here too. So for this question, there could be two answers. But yeah, so you have to find this point to find the gradient. And how do we do that? So let's just quickly use this function. So for example, and let's say we want to find the curve. Well, actually it's a cubic function, so it could be a bit difficult without using a calculator. So since I don't have a calculator with me right now, I'll just use a quadratic formula. Wait, but quadratic formula is too simple. Okay, I'll just stick to this and then tell you how to do it. So let's say we want to find, yeah, so let's say the point is here, -2 and 4. So clearly the point does not lie on this function. Alright, so when you insert -2, the function must equal to 0, not 4. So we want to find the tangent on fx where it passes through the point. So let's say it looks like this, let's say. Then we must find this coordinate y. Again, this tangent is a line, so it looks like that. We have the point, but we don't know the gradient. We have to find the gradient, but we don't know this point, right? So what we can try to do is that just let it as t. Then what's this y value? T cubed plus 2t squared, because that's the function. So if we insert t, then that's what we get. And how do we find t? One thing, so what we can try to do is that we already know this coordinate in terms of t, and we have this point, so we can create the equation of the line using this coordinate. What does that mean? So what's the gradient? Rise over run, right? And we have two coordinates, so t cubed plus 2t squared minus 4 over t minus 2. So that's how the gradient will look like. And that's how the gradient will look like. And again, we also know how to find the gradients, right? We differentiate it, and that will yield 3x squared plus 4x. And the gradient at this point will certainly be f prime t, right? And we have the equation of the two equations of the gradient. Then we can equate these because they will yield the same gradient. So we can solve for t. It's a very random question that I made, so I'm not really sure whether the numbers will be very cleaned. So I'll expand it out directly. So we can see that they cancel out. So 2t squared, but we have 6t squared, so 8t squared plus 8t plus 4. Okay. So we can try using factor theorem, but I can't really think of a... Yeah, I don't think it works for this case. Does it? Yep, I'm not really sure. So you can use GDC to find t. But yeah, so once you have this, you can use your calculator and solve, or you can use you can use graph and then find t. And what next? So for the values of t, you can put it back to this equation or this equation to find the gradient, and then you can find the equation of the tangent. And note that it's possible to get multiple values of t, because as you can see, you can sketch more than one tangent. That's why. So yeah, it's absolutely fine. So unless the question has a specific condition on t, then you just write down all the possible tangents, and that's it. But yeah, again, unless you're in HO, you don't really need to know this. It's more like algebra. So that was the second application that we can have for differentiation. And now the third one is kinematics, that a lot of students don't really like. So what's kinematics? So in physics, so all those movements related to time. So for example, displacement, which means the position, and velocity, which is speed with direction, and acceleration. So few terminologies that you have to know. Again, displacement, velocity, and acceleration. So for those students who don't know these terms, so displacement basically means distance with direction. So in other words, we can also use position as displacement. So position or coordinate means displacement as well, because it's indicating the position, right? And velocity is, as I said, speed with direction. So these are vector quantities and these are scalar quantities. So distance and speed, they can never be negative. Distance of -3 kilometers, that doesn't make sense, right? But displacement of -3 kilometers makes perfect sense, because it's just at 3 kilometers away at the opposite direction. So and what are the relationships? So if you have taken the basic physics, we know that speed equals to the distance over time, but in fact this is not that precise. What I mean by not precise is that it shouldn't be just distance over time. The speed must be the change of distance over a change of time. Sometimes you can directly use this because the question is assuming that an object started from the origin. That's why origin, that means at time 0, the distance is at 0, the very first, like the starting position. But you may also be asked like that. So you have a certain distance, so from like 3 to 7 at t equals to 1 to 2, then in that case you have to use this. So this one is actually using this, but the fact that it's just the origin, so it doesn't affect. Right, so then why is this related to calculus? Is because this time, this delta, we've seen a lot, right? We've seen in the previous class, previous video. So that's looking for the gradient. So what this is saying is that if you can sketch a distance by time graph, then the gradient must be the speed. That's it. But as I said, speed cannot be negative, right? So even if the gradient, there's nothing here, because time starts from 0. So even if the distance graph looks like that, what is this? Negative, right? Negative speed doesn't make sense. So what we can do is that we use velocity, so displacement. So displacement, time, and displacement, and usually we use S for displacement, velocity, acceleration, distance, and speed. So displacement can be negative, so let's say it looks like that. Then the gradient here is basically the velocity. And same thing, so if we have an equation of the gradient like equation of the velocity like this, then all these gradients is the acceleration. Then how do we apply calculus differentiation to find this? So once you have a displacement, if you differentiate it in respect to time, remember always time, then you have velocity. And if you differentiate velocity by time, it gives you the acceleration. So it's very important to note that these work. So velocity equals to ds over dt and acceleration equals to dv over dt works if and only if the function is differentiated by time, nothing else, time. So a very difficult question that you may get sometimes is something like this. So wait, before that, I'll just keep it simple. So for example, let's say you have an equation of displacement like t cubed minus 2t squared plus 1, let's say. Then if you're asked to find the velocity, equation of the velocity, then you differentiate by t. So it's 3t squared minus 4t, done. And if you want to find the acceleration, then what is this? It's the second derivative that we've done. So 6t minus 4. So that's velocity, and that's dv over dt, which is the acceleration. So this is how you can compute the equation of the velocity and acceleration. And the hard case that I'm going to talk about is something like this. So this A is acceleration. Now, what's the difference? This is in terms of t. So we could directly differentiate it, right? And then obtain velocity and acceleration. But here, this s is the displacement. So it's entirely fine, absolutely fine to have an equation of velocity in terms of displacement if you do some advanced physics. But our problem is that we only know how to compute acceleration by differentiating velocity by time. But this is in s. So if we differentiate by time, this is time, this is s. So you may try to use, so what do you need to use here is that you can't differentiate it directly. And what's this? We use chain rule. Why? We can't differentiate directly because the variables are not synchronized. Then we find a way to synchronize the variable. So we switch this. And so we are basically differentiating s squared minus 4s by s. Makes perfect sense. We have this. And ds over dt. Okay, what's ds over dt? It means we differentiate displacement by time, and that's exactly the velocity. And we know the equation of the velocity, right? Done. dv over dt. It's acceleration, and we have the equation of s, and s equals to 5. So we just put that in, and we're done. So that's it for kinematics. But so one thing to remind you is that kinematics is often hard because there are some like terminologies that you have to understand. So for example, like so the typical thing is like find the time where the ball is at rest when it's vertically thrown upward. That means so vertically thrown upward, so the ball goes like that, and since we have gravity, the ball reaches the maximum height and it falls back, right? And this is where the ball is at rest. So really you have to get some experience in kinematics in order to be more familiar to the wordings, and so that you don't get confused. So that's it for kinematics. And now the next application. Alright, so this is where most students find it difficult. Rate of change. So kinematics is also an example of rate of change, because what rate of change means, so rate, what does that mean? It involves time, right? And clearly if you have taken like basic chemistry, so rate of reaction, so you look for the reaction under time, so denominator as time always. And change of what depends on the question, so change of an object, so for example maybe population or volume, radius, height, anything. So the question may ask you to find the rate of change in radius. That means you have to find dr over dt. Change of rate of change of population, then if you let p as population, then dp over dt, so on. The reason why this type of question is difficult is because the question is long, so often there are like a lot of conditions in the question, and also very likely you have to derive the functions by yourself. So remember all these examples, we have the functions, right? At least the functions were guaranteed in the question, so we had functions all the time. But this time you have to find your own function. So very simple rate of change is something like this. So volume of a sphere is increasing at a rate of 80 cm cubed per second, and at what rate is the radius increasing when the radius is 4 cm? So again, there are many conditions, so what I recommend you guys to do is that write down all the conditions out. And what I mean by write them out is not word by word, like not exactly word by word, but write it as in derivative. So first, volume of a sphere is increasing at a rate of 80 cm cubed per second. Then clearly it's the rate of change in volume. So if we let v as volume, dv over dt equals to 80 cm cubed per second. And the question is asking you to find the rate of the radius increasing. So rate of radius increasing, that means we have to find dr over dt. But at what? When the radius is at 4 cm. So that's the given condition. And one more condition given, the volume is a sphere. Then the reason why this question is simple is because the equation is simple to get. So sphere, then very simple, right? Volume of sphere is this. We all know it. And we just need to use these conditions to find dr over dt. So here we have the equation, and we have dv over dt. And on the left side we have v. Then if we want to use this, why don't we differentiate both sides by t? Oh, and one thing, so whenever I just said differentiate both sides by dt, right? So that means we have this. So and this d over dt is just the same as like any other notation. So for example, if you want to square both sides, what do? You just square it like this, right? If you want to root both sides, then you root it. And if you want to take natural log on both sides, then that's absolutely fine, right? It's the same for derivative. So if we want to differentiate both sides by some like a specific variable, then it's also the equality still holds, okay? Unless the function is indifferentiable, but that's what you're going to learn in IBHL calculus options. So you don't have to worry about it, because for your syllabus, you'll always be given with differentiable functions. But anyway, so we have this. So dv over dt is 80. So we put 80 there. Now, 4 pi over 3 is a constant, so let's take it out. And we have dr cubed over dt. And what is this? Again, we use chain rule. Why? We have a function in r, but we're differentiating it by time. The variables are not synchronized. So in order to differentiate it, we use chain rule to differentiate. And one thing, a lot of students, sometimes I saw some students doing this. So r cubed is r times r squared. So they treat r squared as a constant, so they move it out and then they make it like d over dt like this. So they make it like that and then use that to solve it. That's wrong, entirely wrong, because again, r is not a constant. You can only do this when it's not a variable, but clearly r is a variable here, so we cannot do this. We cannot take it out. So we use chain rule by multiplying 1, so it doesn't affect the equation, and rearrange this a bit, so we have this. So r cubed differentiate by r, that's deadly simple, so it's just 3r squared, and dr over dt, we don't know it, but it's fine because we're just looking for it. So we have r here, and we're given with r, right? So these three cancel, and r is 4, so 16, so 64 pi. So dr over dt, so you move everything there, 64 pi, which yields what? Yeah, so this is what we have. And last thing, unit. Done. So that's how we do it. And also for kinematics that we've done, once you put this back, you have to write the unit as well. Don't forget the unit. So that's the rate of change. Very, very, very simple example of rate of change. For IGCSE students, you have to know the percentage increase in respect to the instantaneous change in x or a variable. I'm going to talk about that later in the other video for IGCSE only. But yeah, so for SL and HL, for SL, probably this is what you get. But for HL, you later when you learn implicit differentiation, where you have to differentiate with multiple variables, and in that case, rate of change could be a bit difficult, but it's fine. But for both SL and HL, I'll give you a very difficult question like this. So, for example, let's say there's like a light, and there's a man walking in, let's say 5 minutes. Okay, 5 minutes per minute, and it's at night, so there's a shadow projected by the person, and that is let's say 5 meters, and no, 10 meters, and let's say this is the man is 2 meters, and it asks you to find the rate of the shadow increasing. The question itself doesn't look that difficult, right? So I've already sketched the diagram for you, and you have a very simple conditions, and yeah, it doesn't seem to be that hard. So that's the shadow. So we just need to find how this length is increasing. But this question can be a bit difficult if you can't look at the diagram carefully. So first, as I said, write every condition down using derivative. So the rate of the shadow increasing, we don't know. So let's say, and so we have to define the variables properly. So this one, 5 meters per minute, is the speed of this guy walking away from this wall. And how do we write that? So for example, then this distance is increasing by this, right? He's moving away, so that's the speed. This increasing is that. So let's say this as x. Then dx over dt is 5 meters per minute. All right. Now you have 10 meters there, 2 meters here. look at the diagram carefully and try to find the rate of shadow increasing. And I will not answer in this video, but if you want to know the answer, then you can leave a comment, or you can try it by yourself. I'll leave the answer in the very end of this video. So that was for rate of change. And now the last application is optimization with constraints. So optimization, basically looking for either maximum or minimum depending on the case. So for example, if we have to minimize the cost, then that's also optimization. Or for example, maximize the profit, that's also optimization, right? But just the fact that we have a constraint. So what kind of constraint? So I'll give you an example. So let's say we have a function like y equals x cubed plus 1, and we want to find the points on this curve where it's the closest to the point 2, 3. So we see that 2, 3 doesn't lie on this curve. So it's similar to that special tangent question, but it's not that difficult. So I mean, this one is not that difficult. So y equals x cubed plus 1, if you can sketch it again, it's always better if to put a sketch next to you and try the question. So that's where, and 2, okay, it kind of looks okay. Alright, sorry, I'll sketch it again. Alright, never mind. So it's up there. When it's 2, it's way up there, 9. But yeah, so this is what it looks like. So this is where the point is, 2, 3, 2, 3. And we want to find the point on this curve where it's the closest. So we don't know which point that it is, right? So let's say we have a point P. And this point P, we have no idea. So let's say the x-coordinate is t. Then since the function is x cubed plus 1, so if x equals to 3, if x equals to t, then t cubed plus 1. Right. And if the 2 points are the closest, that means the distance between them must be minimized. So let's create an equation of the distance here. So distance equation of the distance will look like this. So yeah, that's what we have. If you want, you can do some rearrangement to like take t minus 2 squared out, because you actually, you can't really do it. And yeah, it's also much better if you just leave it like that and use chain rule. So let's use chain rule. So okay, distance, I'll use capital D. So we differentiate in respect to t here. It's not time, it's just like x. So if we use chain rule, we take out half, make the entire thing as negative half, and you differentiate inside. So you can slowly do it more slowly using chain rule. So you should get this result if you use chain rule. So the same. So we have half here and we see a lot of 2's here. So let's try to cancel that out. So t minus 2 plus, so we canceled out 1, 2. So it leaves 1, 2. So we have this. And this, we are trying to find the minimum distance, right? So like what we did for maximum and minimum, we first find the stationary point. Note that the denominator cannot be 0, right? So we don't really consider this. We just look for the numerator. So if we expand this out, 2t cubed minus 4t plus 2 minus t minus 2. Okay, I tried to make it as a clear number, but seems like I can't use I can't use factor theorem, I think. Can I? 16 minus 8. Right, no, not really. Okay, so let's say using a calculator, you got certain values. So let's say A, B, and C. Let's say. Then, so I'm not quite sure, but let's say we have these 3 roots. And again, how do we do it? So in order to justify a maximum or minimum, we've learned 2 methods, right? So one is the first derivative test, and the second one was the second derivative test. But in order to use second derivative test, you have to differentiate this again. And clearly, I don't think that's desirable. Well, if you have a calculator, it shouldn't be that hard. But even if you have calculator, it will consume a lot of time putting it into the calculator. So first, if we use first derivative test, we don't really have to care about the denominator at all. So why don't we just use first derivative test, project a table, and so d over dt. So we see that let's say it looks like this, just in case. So it's negative when it's less than a, and it's positive between a and b, and it's again negative between b and c, and it's positive again after c. So that means in the original function, the distance, it's going down, going up, going down, going up. Minimum, maximum, minimum. Okay, clearly I think the graph must be wrong because we shouldn't have, well, it's possible to get 2 values, it's fine, but yeah. So anyway, we justify at which t the distance becomes minimum, and then for this case, for this particular case, we have 2 values, right? So put those in, and that's not it. Once you put those in, we compare, because closest, right? So there could be, I mean, these 2 values could be different. So yep, so that's the cubic function. So in the proper original function, it may look like that. So that's why we have minimum, maximum, and minimum for the original function. So you see that these 2 minimum have different values. So this one is lower, then we could go for that. So that's how we can do this optimization with constraints. The reason why this, so the 3, the reason why these 3 are considered difficult, I mean especially these 2 are considered the most difficult, is because you have to derive your own equation like this or this. It's very rare. I don't think for IB you have to do this, but well, it's possible to have it because it's basically using a similar triangle to find the equation. And one thing, yeah, and also for this you have to find your own function equation, but this one was simple. But yeah, so that's why optimization and rate of change are considered difficult. So what I recommend you to do, especially for rate of change, is that again, write down all the conditions first. So analyze the question first, understand and analyze the question first, and write everything down in terms of derivative, so that later on you will know what to differentiate and which variable to differentiate with. Okay, so that's it for today, and for today's lesson we covered the 5 main application of differentiation. But this is not it for HO students. So as I just showed you a bit, so for HO you have to do further trig formula, so all these like secant, cosecant, and cotangent, and also inverse trigonometric function. So when you need this, and lastly you have to do implicit differentiation again. And once you learn implicit differentiation, I'll come back to these application, especially this tangent and normal, and rate of change, because a lot of cases you may have a function with 2 variables, x and y, so you have to use chain rule well to do that. So what I mean by implicit differentiation is that, for example, you have something like this, and you have to find dy over dx, and some students get confused because it's very different with what we have done so far, and there's no way, for example there's no way you can write y in terms of x. Okay, so in the next video I'll talk about these for HO students. And for SL students, I think that's it for your syllabus. Yeah, that's it for your syllabus. So you just need to, you're done with differentiation. Alright, so see you next time. Bye.